Right. So about a week ago, or maybe a little bit longer than a week ago, I made a video where I demonstrated how you could write some kind of horrible program in Prolog. What the hell did I? Oh, I made a cryptography program in Prolog. That's right. So I'm opening up Visual Studio Code again, only it's not the right size, is it? It needs to be there. You might not have even seen anything, but it's bigger now, and I could even make it bigger if I wanted to. I could make it as big as I want or as small as I want. And that's easy. You can hear my keyboard. I use the loudest keyboard available on the market, and that means that you're going to hear it very well. Yes. So I wrote a program in Prolog last week, and the kinds of comments I made about Prolog effectively amounted to, we don't know how Prolog works. It's a mystery. We have no idea, and don't ask me to explain it. And that's not really true. I wouldn't have been capable of writing the program if I had no idea how Prolog worked. The problem is that I'm completely incompetent at explaining it. Now, there are online resources that explain Prolog very well. My favorite one, which is just based, I suppose, on personal preference and familiarity, is William Mitchell's guide from the University of Arizona, which is easily found on Google, but I'll be sure to include a link to it. The other way that you could choose to learn Prolog, though, is you could write your own Prolog. So exactly one person mentioned to me in any capacity that they watched my previous video, which I assume means that exactly one person is listening to this now, and it's probably you, whoever that is that you are. And that person told me that they really wanted to learn Prolog, but they just don't have any time because they're constantly doing things other than learning Prolog. But before they really wanted to learn Prolog, they really wanted to learn Haskell, and they didn't learn that either. So today we're going to be building Prolog, but we're going to be building it in Haskell, meaning that after this video you should understand both Prolog and Haskell poorly because I won't explain it well. So the Haskell build system is called Cabal. There's another one called Stack, and there's probably more of them that I don't know about. It seems like they have a very short life cycle. But we're going to be using Cabal. I'm hitting some buttons. Those buttons don't make Cabal appear. Those buttons make Discord go away, which is exactly what I want because Discord won't help me with this video. So we set up Cabal, and we tell Cabal we would like a project. And this is, of course, the thing that every programming language has now as a tool that asks you unhelpful questions until you have a project. So I can decide on important things like which version of the Cabal, I assume the file format for the build tools to use. That's 3.0, and Prolog is as good a name as any for our Prolog implementation. Okay, fine. I'll choose a different name. Pyrex Prolog. Obviously, this makes absolutely no difference to me. I'm not going to publish this to anywhere where anybody else could use it. It would be bad for me to do that because they shouldn't use it. We'll have a default package version. We'll use the. I have no issue with this license. Is it the one I would have chosen? Well, not when you give me 17 options. I don't know. What's the first one that got cut off? I guess I like the BSD3 clause fine. And my name is still Neogme or occasionally Pyrex. That is still my email address. That's useful to know. And I don't know or care about the answers to any of these questions. They are frightening to me. This one actually does matter. Our program will start by invoking main.hs, which is a file that we will provide. We can decide which version of the compiler we would like to support. That's not quite accurate. Haskell itself as a language is versioned, and in theory, we could support a version that is relatively stable, that's been the way it is for a really long time, or we could pick an experimental version. We're not going to be using any experimental features because we're not doing anything that would require them. So we'll stick to the old version, and we'll keep the informative comments, which may help me in some way. Or they might not. Difficult to say. So this is the file that was just generated for us. Our project now has this perfect file that's very useful to us. We can see it right here. It's beautiful. We're going to be making some changes to this file. There's a few specific things I want to look for. You'll notice that we have a list of dependencies that our project is associated with. And this is actually populated by Cabal based on what version of the compiler you have installed when you invoke Cabal, which isn't likely to cause you any problems because you're probably going to be compiling with the version of the compiler that you had installed. But because Haskell uses very aggressive semantic versioning for its standard library, you might potentially want to change the constraint on base, which is the standard library. So we're bringing in one other thing. By the way, the fancy pile of weird sigils here, the one that looks like a crocodile eating another crocodile, that is just how you stipulate to Haskell that you want it to approximately match the version. I don't remember exactly how Haskell implements this constraint, but it does. So beautiful. We've done some basic project setup. This took longer than you'd expect the first time because I switched compiler versions midway through. Oh, that's the Haskell plugin, which is useful. It's useful. It has some problems. We'll see those problems later because I assume they won't have fixed it since the roughly 6 hours ago that I wrote the project code. So one of the things that we can do now that we have our project and we have this Hello World program that I didn't write and it looks great, we'll see that, yes, it has a bunch of build steps. Those build steps are, of course, still true. They don't change. Right. So the first thing we'll do is we'll just change our main program to look slightly different so that we have a scaffold that we can use for the rest. That's actually all I think I want to change right now. In theory, I could change more. That looks fine. So the first thing we're going to do, and this is going to look a lot like what we had to do for the Prolog program, because I guess the way that I write programs, especially when I have reference material from a previous attempt, is usually the same. We're going to write down some data types that represent values in Prolog, which Prolog idiosyncratically calls terms. Right. So we've got atoms, and the word atom in this case refers to a value that can't be divided up any further. I'll give you an example of an atom right now in the expression hello world, which is a valid Prolog term. Here's an atom. We also could divide this up like this. That's an atomic value, or we would say that, like, actually, I shouldn't say this definitively. I've done logic programming languages a few times. This is the gap in naming that I historically use, but I'm not sure if it's standard or if it's a thing that I came up with in order to simplify the problem for myself. In general, when implementing a logic programming language, I would use this nomenclature. Regardless, in this case, we're actually going to be using the word atom consistently here, or I guess we might as well. Although I'm very tempted to just be more consistent. Let's continue here. I'll show you a few other things. We're going to have terms. So I've given you one of the two forms that terms are allowed to take. The other form that a term is allowed to take is like this. Something you might remember from the previous Prolog video is if we have an expression like hx, we can write a statement like hx equals h world, which this has the effect of making x equal to world. That's an example of a thing that you can write. This is actually how you write a comment in Prolog. Beautiful. Okay, so we've got here is a term that is a variable. I'll just include an explanation of that. And it's fairly important that you understand this, which is a problem because I don't have time to do too much review on it. The gist of it is that a Prolog program can be accounted for by compound values or compound terms and variables. Right. So we've got a data type representing a variable. Of course, we haven't actually made that data type yet. I'm giving this the name vint because this constructor, I don't want this to have the same name as this other constructor. When we actually invoke these, it'll become more obvious that these names should be close to being unique across the program. I guess the other option would be to do it like this, and that makes it clear. A variable is associated with a slot that it lives in. We'll go with that. Actually, we probably don't need the word constraint. So this is just saying to Haskell, hey, we'd like you to generate default implementations of the equals operator, which does the same thing as it does in C, which Haskell will gleefully do, and the show function, which is equivalent to toString in Java. Beautiful. And now you maybe understand that. We'll get rid of all of these annotations that we've left lying around the file. because we don't really need them. Yes, we might add more things to this file later, but this is actually the basic set of values that can account for everything in a Prolog program, at least as we're defining Prolog. We're implementing a subset of Prolog. So one of the things that Haskell does that is very similar to Prolog is that you make a list of things that you're exporting. Exporting, the word export also, I'm sorry, I just want my names to be short. We're going to go back to the previous name. Things that we export are the only things that are visible to other parts of the program. Now, we're actually going to be exporting nearly everything. But for instance, like if I were to define a second data type, yes, this isn't a very useful data type. We'd never use this. But we might elect to define it, but not give anybody else access to it. We might only use it inside the terms folder. Or sorry, not the terms folder, the terms module. And if we were to do that, then we would deliberately not export it. This is important in Haskell because many things become names in the unqualified scope, which means that, for instance, in a language like Rust, you might have to refer to term pamayim nekudatayim compound. You might have to refer to it that way. Whereas in Haskell, you just have to refer to it like this. And in fact, you're not allowed to refer to it the first way. They may have done something about this since I learned Haskell. I'm not actually sure if they have. Haskell is another language that I avoid using, and that's probably not fair to it. It's not nearly as, we'll say, difficult to make practical use of as Prolog is. But it's not a language that I really like very much, and it's a language that causes me a lot of frustration, and therefore I'm not always up to date on the tools. That being said, this is a pretty accurate representation of Prolog terms. So we're going to click around a little bit. There's one other thing I want to draw attention to, which is that let's say that I write a binding like this. X is a string, x is equal to 1. You'll notice that nothing complained, and that's really interesting because we are using the Haskell language server, which is specifically intended to complain about these things. Now, the experience I was having earlier, and I don't know if this is an intended behavior or if I'm just not lucky, is that I had to restart the Haskell language server every single time I updated the Cabal file here, because it wouldn't be very helpful. Now, we can see that once we restarted it, which takes several seconds, it correctly complained about this binding. That, as you can see, that I would complain about this binding. We've set x as a string, and we've set it to a value that is very much not text. A string should be text. So, okay, now we've got the language server running again. Maybe we find that to be really exciting. So we're going to be defining Prolog in a way that resembles the strategies used to implement Prolog in C. The problem is that Haskell doesn't have a whole lot in common with C. So we're going to have to build a substrate that is consistent with the design of C. I don't know if I like this name primitives, but I think I'll go with it. We'll say that these primitive operations are the operations that that you would expect to be provided by any language that could be used to implement Haskell. So instance sigs is just an extension that lets me write a greater number of type hints than I would ordinarily do. And the reason that I want to do that is because I'm going to be explaining these types as I go. It would help for me to put them on screen for you. So Haskell has a data type named IO. I'll remind you of it in a moment. The very first thing we're going to do is we're going to define a data type that is similar to IO, but gives us a few more features than we would otherwise have. So this is the type of a function, specifically run Prolog IO. In addition to being the name of the only field of this type, is a function of type globals to IOA. Now what this actually means is that there is now a function at the module level called this, and it has this type. We might get into what this type means. I might just ask you to take it on faith that this type makes sense or learn it by example. But for now, we'll say that this is the type of the function, and that might be, you might be able to justify it by observing this is an accessor on Prolog IO. It gets the extra argument that goes on the left-hand side, which is the name of the Prolog IO type. it gets this extra argument here. This is the self argument of the accessor. And then, of course, the return value is this type. You could also spell this type like this. They mean the exact same thing in Haskell. This is called currying by default. It's one of the flagship features of the language. I suppose I should devote a little bit of time to that. We'll see if I can get around to it. But for starters, we've got this type. It is mostly compatible with the IO type built into Haskell. Actually, that's not true at all. It can be made to be compatible with the IO type built into Haskell. We're going to actually have to define that compatibility explicitly. So we'll be defining a type class. Now, what this says is that if I've got a value of type M and it can hold on to an A, then it should be possible to define, or basically this is a function that anybody who wants to can define from their type, which implements the monad interface, which I'll describe what that interface means in a little bit. It's a built-in interface to Haskell. It's used a lot. You can convert a value of any type implementing this trait to IO. So I'll implement this, and that will be a good example of what it means. This type would almost always be something more specific. Oh, this is actually exactly backwards. Not that you would have any reason to know that that's backwards because you don't really know what this function does yet. We do have to also do a little bit of bureaucracy before I can even show you what it does, don't we? So we'll introduce it into this file. Now we have that perfectly documented in that file. Oh, nice. This is copyrighted by me. That's useful for me because I might need my copyright. We'll restart the Haskell language server as before because that program is not helpful to us. So the actual meaning of this is that we can write a specific function. Now, is it going to, it should be complaining at this point that I haven't written this declaration yet. Well, it's complaining about something. What's it complaining? Oh, it's just complaining that I didn't spell module yet. So the exact function that we're going to be writing is this. The idea of this function is that if you have a value in Haskell's default IO type, and you want to convert it to a function that uses that is a value of this new Prolog IO type, the conversion is in fact possible. And the reason that I've defined this as a type class is because I'm very likely to use this for other types. I might want to have a similar conversion between IO and, well, you'll see there's going to be another type that looks very similar to this but isn't the same, and it would support the same conversion. Now, we're fortunate that we can just see the definition right up there. So a Prolog IO contains a function that takes a globals and it produces an IO value. We happen to have an IO value, and we return it. There, see, look at that there, and that type checks. We're going to see if it's actually type checking or if the Haskell language server it fell asleep again, didn't it? Or did I just forget to put this file on the list? Did I? Oh, I forgot to put the file on the list. That would be why. Okay, yeah. We're going to wake up the Haskell language server, and then this is going to become a type error again, and I'm going to be relieved. If you want a language that doesn't have these tooling issues, but otherwise resembles Haskell, by the way, like, you know, Rust is free. You can just use Rust. You wouldn't be able to write this program in Rust. You're going to quickly see this program is in a style that's completely incompatible with the way that Rust is designed. And I suppose that part of why I'm doing that is because I want to show off why Haskell is at least ostensibly good and cool. But in general, you can do a lot of the same things that you do in Haskell and Rust. It has a very similar type system. That's not entirely fair. Haskell has a type system a lot like Rust with a lot of inconsistencies of Rust. Not really removed, but just not in existence. It turns out that having a garbage collector means that most of the complexity of Rust just kind of goes away. In addition to that, having purely functional semantics gets rid of a lot of complexity that Rust has. Purely functional semantics meaning that I can't mutate. I can't take an existing value and modify its fields. I can only make a new value. That's kind of the flagship feature of Haskell. People like that feature, ostensibly. So I probably should actually define my globals type here. We don't yet know what we want to put in this. I mean, I do because I wrote the program, but you don't know that. So the gist of it is it's a function taking this globals value, which is apparently of absolutely critical importance, whatever it means. What we now need to do is we need to implement some other interfaces that are helpfully built into Haskell. These interfaces are kind of tricky. Again, the reason I'm using instance sig is so that I can write this line, which specifies if I were to implement this interface, what does it mean? You'll notice I'm insistently using the word interface, by the way. Haskell uses the word type class. A lot of people get tripped up on that because when Haskell says class, they mean something very, very close to what Rust means by trait. And if you don't know Rust or Haskell, you might instead know the word interface, which is what Java uses for its own very similar concept. There are some important differences basically in that interfaces in Java always provide one self argument, which is the first argument, and it's used to determine what interface is resolved. Whereas in Haskell, interfaces, or I should say type classes, don't specify anything about the position of the self argument. I can go back here and explain that. You'll remember that for a while I was writing it like this. So this is very interesting because the type of self is M. We've named it M. And as you can see here, it's on the right side, and here it's on the left side. So like these are both valid. These are both allowed. But you can only write, out of these two, you can only write this one in Java because this is the only one that has the self argument on the left as an argument. This is a self return value, which is not expressible. Anyway, that's just one of the legitimately super cool type system things that Haskell does that I kind of wish every other language would pick up. It kind of sucks that Rust is like I shouldn't say Rust is the only major language to do this. I think Swift may have picked this up too. For all I know, maybe Kotlin or Scala has it at this point. That wouldn't surprise me. I have to admit, I never really caught on to Scala because the community has a certain reputation of horrible bigotry, which I don't know if that's deserved, but it scares me. It's probably not deserved. Like, Lichess is written in it, and there's no way those guys are bigots. They make fantastic software. At any rate, so we'll continue to write utility functions. I'll explain why this works in a moment. You kind of have to... Oh, by the way, I'm going to follow a Haskell idiom, which is that if you don't use a variable, you're going to rename it, and you're not going to have it have a name. You're going to have it be named underscore, which means this isn't a variable name. This is just a wildcard that gets thrown away. As a side note, you'll notice that like in this interface, we explicitly said it has to implement monad for this interface to work, and we haven't actually implemented monad yet, so that's going to be a problem for us. We'll get around to that. So the gist of it is that A is a function taking globals. So we're going to put globals into A after we get it from this function that we're defining here. So this function is the body of run Prolog IO, which of course exists up here. We take the globals, we put it into the function here, which has the exact same type. The only difference is that, because this is a generic type and we're passing a function from A to B, we're going from a Prolog IO of A to a Prolog IO of B. If that kind of goes past you, like the way that you'd write these types in Rust or Java is you'd write something like this. This is not how it would be spelled in Rust, actually. It'd be spelled something like this. Yeah, so this type means the same thing as what I just wrote here. You'd probably actually write it like this because Rust cares about what flavor of function pointer you have in a way that Haskell... There's literally 6 different flavors of this that you could write. No, there's 8 different flavors of this. No, there's 7 different flavors of this that you could write in Rust. There is a number of different flavors, and in Haskell they're all the exact same flavor because Haskell doesn't care about lifetimes and Haskell doesn't care about mutability. It doesn't have those features. So anyway, the type of fmap stays nice and very simple. This is one of the reasons that Haskell can do things like async super well, because in Rust you need a zoo of memory management features and very specific features to constrain shared mutability, like fucking pin. Who even understands what pin does? Not me. It becomes very complicated. So the gist of these interfaces, you can't really explain what they do that much better than you can explain just by kind of pointing at their types. Um, there's something else called the applicative laws and monad laws that is also relevant to these interfaces, but I'm just going to kind of be gesturing at these types and saying, if you get it, you get it. There's a great article on these types called the Type Classopedia, which is spelled the way that it sounds like it should be spelled. It's like the word encyclopedia and the word type class grafted together. And that kind of explains how these types are expected to behave. But like if you stare at the data type real closely, you might get an idea of it. So this one's a little cryptic. The gist of it is that as before, we are taking a value that's not a Prolog IO and we're building a Prolog IO using it. The distinction here is that like while functor is about taking a Prolog IO of A and turning it into a Prolog IO of B, this is just turning an A into a Prolog IO of A. This is effectively the same as like taking an integer and putting it into a list of integers, except Prolog IO does something very different than what list does. Prolog IO is basically, it is a variation on IO, which is Haskell's wrapper type for operations that do IO. The gist of it is that IO of A itself, like you could have an IO of a string, for instance, which is the type of an operation that does an input-output operation resulting in a string. And there are operations on IO operations that sequence them and cause them to be done such that, for instance, I'll divert very quickly into explaining IO, and then I'll explain what this type means again. Let's say that I've got a type T, or we'll be more concrete. Read file manual.text has type of IO of string. We might also have write file, this is the manual. Manual.text is also IO of string. We'll say that this is an operation called read it. This is an operation called write it. So the gist of it is that Haskell has the ability to write these two separate programs, and like they don't have the same meaning at all. We would probably want to print it to the screen. So yeah, you could write something like this. So by the way, if you're wondering, this is the type of put string line. So for instance, this program here would have the effect of reading the file, printing it to the screen, and then writing new content to the file. This would have the behavior of writing to the file, then reading content from the file and putting it to the screen. And these are programs written using the monad interface that we talked about earlier. The fact that it's the monad interface isn't really that important. It's just that's the interface that happens to be being used. So these programs are exactly equivalent to these short programs, which there's a lot of syntax here. I'll be writing code that looks a lot like this shortly. For now, it might just help to think. This is how you string IO operations together in Haskell. These could also, by the way, be written in this much cleaner way, which lots of people understand. We're going to have no shortage of code like this in this particular program, so you might have some fun understanding it. Also, I'm 90% sure at least one of the versions of the program that I wrote was total bupkis, but we'll see. So anyway, we're defining a function that takes a thing and puts it in the IO box. And that's useful because if we put it in the IO box, we can use Haskell's sequencing tools on it. These interfaces are all connected to the sequencing tools that Haskell has. So we'll write a few more of them. By the way, these are going to get increasingly exotic, and I'll tell you why in a little bit, but we aren't getting to the really exotic part yet. Like, there's a reason that I keep fear-mongering about these particular interfaces, and that's because what we do with these interfaces has an extreme effect on the behavior of the rest of the program. Anyway, as it stands, so the gist of it is that if we want to take a function that is in the IO box and apply it to a value that is in the IO box, we would write this series of statements. This is, I've just shown you the do interface. This is the do interface as it applies to the IO type, which is underlying. As a reminder, the idea of Prolog IO is that it is literally just a wrapper for a function that takes a global and produces an IO. So like once we've written this, this value, this f globals value is literally just a value of type IO. Oh crap, the tool isn't going to actually show me the type. It'll show me this type. See, f is just a function that takes a value of globals and puts out a value of type IO, a function of a of b. So that's a function from a to b inside the IO box. X is just a value of a. It would make sense that we could take the a, put it into the function here, and the only thing stopping us is that we have to go through Haskell's specific sequencing for IO operations API. Maybe something that I could have drawn more attention to is that, like, the reason that Haskell needs this API for sequencing operations is that Haskell allows operations by default to be reordered arbitrarily. So, like, if I were to write this program, x equals 1 plus 2, or sorry, we'll say let x equals, we'll do it in the standard way that Haskell would. We'll say that let z equals x plus y, or we don't have to use z in this case, or sorry, let in this case. So z is an int, z equals x plus y, where x equals 1 plus 2, y equals 2 plus 3. There is an evaluation order, and the evaluation order is that x has to be done before z because x is incorporated into z. Likewise, y has to be done before z because y is incorporated into z. But there's absolutely no rule saying when x should be done with respect to y. And in general, Haskell will evaluate values at the latest time possible. So like if I were to say z equals 1, 2, we can do this very quickly in the main module because we still happen to have the main module. I'll comment this out so I can show you. Right, we've got this. If it's not obvious, I have a huge amount of affection for Haskell. Part of why I complain about it so much is that I like it. So we'll say message is a string, message equals, and by the way, this is just a party trick. This is relevant to understanding Haskell. If you understand why the things that I'm doing work, you understand Haskell. And if you don't understand it, you need to understand how Haskell works. But this isn't an important part of how you would normally write Haskell. So to start with, like this part, there's no magic here. It's obvious why this would work. And we could, for instance, say, okay, so it just says hello. We'll say that the suffix is equal to, sorry, this isn't the part that's magic. This is the part that's normal and anybody can understand it. If you're wondering, by the way, how I type so fast, I'm using Vim bindings, which make things a lot easier. Right, so that's the whole message, and that's the first 6 characters of the message. There's nothing stopping us from saying error what the heck, which is, of course, a function that has the behavior of crashing once you evaluate it. But as you can see, we don't see the crash. Maybe you're wondering, well, how do I know I don't see the crash? Because I don't know what the crash would look like. Here's the crash. You can see that, yep, it says, oh, here's a big backtrace, which maybe you like this backtrace. Maybe this backtrace makes you feel really good about knowing that my program exploded. There's, of course, also nothing stopping me from saying something like this. So message will have the effect of calling the function message when it's done. Oh, yeah. So this is a recursive function that will not stop recursing, but it will only be evaluated as deeply as it needs to be. So anyway, the idea is that Haskell has this do notation and this alternate set of functions for sequencing operations such that those operations can be made to depend on each other. You'll notice that message being a string is effectively a linked list. In fact, in Haskell, the default string type is literally a linked list of characters. Anyway, to clarify that, like, because string is literally a linked list, you do have to, it'll help if I show you directly. So if we were to represent the string XYZ, it's equivalent to this. The actual way it's represented, oh, sorry, these should be character literals. Yeah, so the actual way it's represented looks like this syntactically, but these are the exact same. We can add the parentheses if it helps you to see them. Yes, so these are effectively the same. I've just renamed the functions involved. Um, so even though you may not need the value z immediately, you do have to get as far as this cons in order to look at this value z. You have to figure out that it is a list with 3 elements before you get z. So the effective functions like this, which allow me to do sequencing, for instance, I can say put string line message, put string line, I hope you're well. The effective functions like this is that they force a certain evaluation order by representing your program to Haskell in a format that is as ordered as say the linked list was. It's a very explicit way to add ordering. So we're relying on the fact that this ordering explicitly orders IO operations relative to each other. And if that's surprising to you, well, I'm not going to stop doing things that rely on the behavior, and maybe it will eventually make sense to you. If it doesn't, don't worry about it. Prolog, or not, sorry, not Prolog, Haskell. This is one of the things about Haskell that has a history of tripping people up, and it's kind of recommended that you play with the language, you try to write some simple programs, you teach yourself how it behaves, and you make it become less surprising. I'll emphasize that the examples I just gave you, especially the ones involving error behavior, you do need to understand them to understand how Haskell works, but you would not rely on that behavior in ordinary Haskell use. In ordinary Haskell use, you don't necessarily know what the evaluation order is, but you also don't really care what the evaluation order is. You just care that your program is implemented in a way that is correct, which Haskell can certainly do with a variety of evaluation orders. If your program would not, in any case, if your program would terminate regardless of what order it happens to be run in, you're doing good. It doesn't matter what order Haskell picks, and you'll probably never know. If your program is wrong if it's run in a certain order, then you're probably using the sequencing tools built into IO, meaning that you would never notice because it would always be run in the right order. Basically, if a value is based on another value in Haskell, Haskell needs to evaluate at least enough of that value to figure out the basis relationship. If you ask Haskell to reverse a list, it doesn't have to know what the items in the list are, but it does have to know how big the list is because it has to figure out how big to make the new list. It's that kind of thing. I'm probably making it sound really mysterious. The rules are incredibly systematic and simple, so in fact, it's not actually mysterious. It's just also hard to explain inside the world of Haskell because I can't write a Haskell function that does the thing that Haskell implicitly does without doing the thing explicitly. It can be more easily explained if you actually use Haskell than if you let me tell you about it. So I've written now, these are all of the APIs that are needed for the do syntax that I keep using to be supported for a type. You might not exactly understand the connection between these values and the do syntax. I'll briefly reiterate. I mean, I'll do a little bit better than reiterating. I'll actually write the types. Oh, wow. The Haskell language server is fast and accurate. That is, in fact, the type. Well, hold up. No commands? Well, but I want to see the type. Show me the type. Come on, do it. Yeah, so return is exactly the same function as pure. They do the same thing. They take a value that's not in a box that supports sequencing, and they put the value in the box. Incidentally, if you've ever used promises in JavaScript, promises are another example of an API that does explicit sequencing. This is very close to the promise.then function, and this notation here is very close in behavior to JavaScript's async await. You might also recall that in JavaScript, async await callbacks can be sequenced in they can be in arbitrary order relative to each other. The scheduler decides what order to run your async then callbacks in, except when they're based on each other. When they're based on each other, it has to run them in the order that you use. This is how you write .then in Haskell. Maybe that's helpful. Anyway, this is another time when you want to look at the type to understand. We take a value that's in the Prolog IO box. This is a Prolog IO of A, and we put it in a function that takes an A, but produces a value that is also in the Prolog IO box, and we get a new value that's in the Prolog IO box, and everything's pretty copacetic. That's how you would write this in Rust, but you're probably not using Rust because you're probably using some other language that you can get more done more quickly in. And in that case, you can probably figure out the TypeScript representation. Worst comes to worst, you can ask a large language model and get the wrong answer. But, it's an answer. So we've got this globals type. I haven't talked about what this globals type does. I think that for now I'm going to put an example in there. I'm going to just say that the globals type includes a label, which is a string. This is not even close to what we're actually going to put in there, but hey, there's no harm in it. So we're not going to list the exports yet. We're going to do that in a little bit, but for now we're just going to export absolutely everything. Oh, right, that's redundant. This will actually compile now, and it's not redundant now that we implement its thing. This will compile now because we implement the monad interface, which we said that anything that implements lift.io has to do. If this name seems mysterious, this is the customary name for this function in Haskell. It's a really common function that's provided by several libraries, one of which is vastly more popular than the others. So anyway, we've got all this functionality. You're going to let me split my editor up. Come on, let me split my editor up. Before this video, incidentally, the thing that's got me down on Microsoft today is that they put a bunch of fucking AI upsells into the editor that I had to remove after I updated. Like I had to manually turn them off because they were making, like, you don't want to see that in a video. Come on, nobody wants to see that shit. So I had to quickly get rid of all that stuff. And that was difficult. I had to go into my settings and I had to change all kinds of things. And it felt scary. Like I don't like looking at my settings. Anyway, so we're going to quickly have a demonstration of how you might use this. We could say let some globals equals globals and the label equals friendly bat. Beautiful. How did I misspell this? What did I do? There we are. I just forgot to import it. Right. So now we can put strline. We'll start by doing this in the obvious way. Label of some globals. You'll notice that label is just dumped unceremoniously into the global scope, or rather the unqualified scope. So because this module imports it, it has label. We now see the label come out. We could also write it like this. Yeah, so this would output a slightly different message. This would output, oh, extra space. That's not great. We'll fix the extra space. So one of the things that we could do instead, using our versatile new Prolog.io tool, is that we could say we'll have the action be in the global scope. Right, and I'll put that on your screen so you can see the whole thing. Beautiful. We'll make it a little bigger so you can really see the whole thing. Right, so we have this action here, and if we were to, main is an IO, we should be able to just run this action in the context of IO, right? Like that should be true. But of course we can't because it has not quite the right type. Its type is, sorry, I'm fighting with the Haskell's indenting support. Haskell has semantic indenting, and as you can see, that's a great, oh, that's actually not even what it's complaining about. It's complaining about something else. What's it complaining? Oh, it's complaining about, wow, I fucking hate paren insertion. Terrible feature. I know some people must like it. Error condition? I don't want error condition. I want the Haskell language server to work correctly. I'll just assume that it's fine. So, right, we now have some globals. We like them. And if we just try to sequence action into main, it doesn't work. Why doesn't it work? Because it has type Prolog.io and it needs to be IO. If we run Prolog.io of action, well, that almost works. The problem is that, as you can see, the type of our accessor is globals to IO of A. So we actually have to provide some globals for it to screw with. So as you can see, beautiful. It now runs, it passes these globals to the IO action. The IO action happens to know that these are the globals that it uses. It knows because this argument is right here. So if I wanted to, I could say action 2. I could define an action 2. You'll notice that both Prolog and Haskell have this feature that allows you to hide an extra argument. We'll say, for one, we'll quickly do this. Like we're effectively hiding this extra argument called G's inside of the Prolog IO type that is defined in this file. So like somebody who just writes a Prolog IO doesn't really know that oh God, it's still not right. Hold up a second. What's it complaining? Oh, it's complaining because this should be a string. Sorry, I get very paranoid when I change the indenting because it feels like it shouldn't. It feels like it shouldn't matter, and yet it does. So okay, that's all forgiven. You'll see now that like the action 2 doesn't know that there's this extra argument called globals that gets run in, but action is able to do that because action uses the Prolog IO constructor to create it manually from this G's function, which is, properly, it's a value of type globals. So now I can say me and you, and we quickly see that. It's me, a friendly bat, and it's also you, a friendly bat. So that might be useful. I say it might be useful. I know what I'll be using it for. There's one other thing we can do, by the way. You might remember that we have this. Now, where is it exactly? It's this lift prolog IO function. Where did I define that? Sorry, we have the lift IO function. We haven't seen that yet. So one of the things we can do is we can replace putStrLine with right. Oh, what's it complaining about? Excuse me. Oh, that should be a right. Just assume that when I write a type, I'm not going to get it right the first n times because, of course, I'm not. Oh God, I didn't mean to. Terribly useless. So now we have this lift IO function, which we're supposed to have. We can also say read globals is a function of type prolog IO of string, or we'll say read label to be more specific. Right. So now what we can do is we can write this whole action in this other way. Right. We'll give it a unique name just so that we don't have a warning anymore. So as you can see, it's now completely disguised that the extra argument exists. This is a really common form of abstraction in Haskell. Specifically, very commonly you would not export the Prolog IO constructor. The Prolog IO constructor is this whole bit. You wouldn't export that it's just a hidden argument of type globals, but you would absolutely still use that functionality. So that's an example of a useful, for some definition of useful thing we can do. We're going to now make some more changes to this file, and we're going to be using exactly that pattern. So one of the first things we'll do is we'll make it possible to create a globals. For now, there's not anything interesting about the globals, so this is going to be a very short function. One of the things that we'll be doing is we'll be spelling the name globals correctly. That's pretty important, because if we spell it wrong, we can't use it. We'll be switching to Haskell's indentation convention for that specific line. Now, of course, this doesn't work anymore. Well, we'll just replace this with a generic putStrLine hello Haskell. This is what it said before I made various changes to it. Beautiful. So let's go back to primitives here, which hopefully we find that useful. We've got the ability to make new globals. We've got some more functions that I'll write soon. One of them that I'll write right away is this error prim function. So this is the function that I mentioned earlier that immediately causes Haskell to crash. We could, in theory, define some specific support in this type for logging the function. We could add like maybe an extra argument, which is a function that is called when the error occurs. We could even put that in globals, or we could have it return an extra value, which is the error that happened to have been produced. There's all kinds of things we could do. It's not especially important that we do any of them. We just want to have something that signals when we blow up here. So we'll be playing with that a little bit more in the future. Let's look a little bit at the rest of the problem while we've got the rest of the problem available to us. So one of the big things about Prolog is that it is non-deterministic. That's not exactly true. When people say non-deterministic, other people hear the idea of it being random. What I actually just mean is that functions can return more than once in Prolog. The gist of how it works is that when I produce a value and I give it to my caller is really happy, and my caller just keeps going from where it left off. And if it turns out that it runs into a case where it can't continue anymore, where it's hit the end of its maze and it hasn't found the exit, when there's no further solutions in its depth first search of all of the possible evaluation states the program could be in, it comes back to my function eventually and it says, well, okay, what else can you produce? I think a very important thing to understand is that I talk about my function as if it returns a value, but what my function actually does, or my predicate, if you excuse me, is it creates a set of constraints inside of Prolog's global state. Right now we have nothing in there. This will be replaced eventually with a representation of a set of constraints, which sounds scary. It's actually not at all. It's really simple. Or at least I think it's simple. I'll make it very clear what that is. But for now, we have to implement this undo and redo behavior. So I'm going to start with some functions where you're going to be thinking, how the heck would this ever be implemented? And then it's going to become clear exactly how they're implemented. But for now, I'll just stub them out. So we remember the Prolog IO type. We've already defined it. We're going to be defining a new Prolog stream type, which represents a transaction where certain functions might be retried. And, excuse me, I can't seem to type. Or rather, I can't seem to talk. So we're going to be defining a function that has the behavior of doing its effects forward the first time that it's evaluated and backwards when we come back around to it, which is a strange thing to say, but you'll be able to see how that's implemented when I define the data types for it. We'll also be defining a bridge from the previous type to this. We'll say that if you want to take a Prolog IO action and then do it just very directly inside of a non-determinism transaction, you would, I almost want to name this non-det because that would be clearer, but I'll stick to Prolog stream. That's the name that I used when I wrote this the first time, and I'll get myself confused if I don't. So we've got this forward function. We'll just define this as reversibly do the forward thing. And when it comes to undoing the changes, the backwards direction, this is how you write do nothing in Haskell. Basically, this takes the empty value, the unit value, and puts it into a box of your choice. In this case, it puts it into this kind of box. And the fact that it only puts the thing in the box means that it doesn't do anything else. And that's possibly useful to you. So we've got that whole deal going on. What's going to happen now is I'm going to write some very dense code. And that code may be a little bit confusing, but don't feel too alarmed if you're confused by it. This is probably the most complicated part of the program. And I'll be trying to supply you with an intuition of how Prolog works through it. So the gist of how our runtime will work is that it will run for a while and then occasionally yield value. Sometimes it will just yield no value. That's also allowed. It's allowed, that is, to say that it needs to compute more without producing a value. And we'll be representing the state of our machine with this data type, which is similar to Prolog IO. It's a special box that supports all of Haskell's sequencing operations. And it can basically be in two states. We'll call these the yes state, which means that, actually we'll call it the maybe state, because we don't know if we've run out of values yet. So when it's in the maybe state, it is producing some reason that the answer is maybe, and it is continuing happily along with the Prolog IO implementation. With the Prolog IO. Actually, no, I can explain that much better. I'm on autopilot. I'll switch back from autopilot and look at the type in a moment. The gist of this type is that it's extremely similar to the linked list type that we described earlier. I'll give you an example really fast. First of all, we'll define simple Prolog stream like this. So this is exactly the linked list type. The linked list type could have been defined, actually, now it is. We'll put it down here. So we could either be adding an A to the linked list, or we could do nothing. You'll remember that I said earlier, oh, apologies, that in order to evaluate up to any point in a linked list, we don't need the previous values, but we do need to know the shape of the list. The gist of what I mean by that when I say that is that, like, to figure out that this point is a p maybe, we need to evaluate this thing on the right here. Haskell would normally do that implicitly because evaluation order doesn't matter if you're not doing I/O. But when we add this, of course we actually use Prolog I/O, but when we add I/O, now we have something that demands Haskell's sequencing operations. We can get an A out of this immediately, or we can do more work and we either get another A or we don't get another A. So the idea of the suspend type is that we can ask to do a little bit more work more than once. Anything that produces a Prolog stream can say, I don't know if you'll be getting an A out at the end of this. Right now I've stopped for my own reasons. And then it can force you to chug a little bit on the right branch again and again, all without ever getting to the possibility of the A actually being yielded through the yield state. So that's how we get to this type, and if that's confusing to you, it might be more clear when I write some examples, or you might just have to accept that this behaves in the way that I've described Prolog as behaving in the past. There is one other thing that we should probably do, which is define lift.io for this type. I happen to have the definition on my screen in case I forget it. It's not that complicated, though, relative to some of the things that we've already written. So we'll, as a reminder, we can take an I/O action, which looks something like I/O of A, and we can turn it into a Prolog stream of A. The way that we do this is we take the value on the that we're turning, or we take the I/O operation, we convert it into a Prolog I/O, which we've already defined this for. And then now that we have a Prolog I/O, we lift that the rest of the way, and that's how we would do that. So that part is probably no surprise, given that we knew that we could already do this step and we knew that we could do this step. So it's just the combination of those two steps. One of the things, oh, we actually have added it to the list. Let's restart the language server again. This is going to complain in a moment because we haven't defined monad yet for Prolog stream. So the next thing I'm going to do is actually something that there are many good libraries for in Haskell. This abstraction is called a stream, and I looked at least two libraries while I was writing this to try to understand what I was doing, and came to the conclusion that I understood what I was doing, but that I couldn't easily explain it. You can, if you already know Haskell, you can learn a lot about this yourself by looking at the same kinds of places, and otherwise you might just have an interestingly rough time. And oh, how silly of me. I forgot to include the language extension that means that I'm allowed to write that. Beautiful. Okay, that's looking good. So we will, oh, I wish I could keep this on screen. Maybe I can. I'll carry it with me wherever I go. So we'll be defining a functor instance, which means that we'll provide this function. Which might be a useful function. Oh, wow, I need to type a little bit better than that, huh? Yeah. So we've got this function. We can take the function that we have here, and we've got two constructors. We've got this maybe constructor, and we've got a no constructor. We'll just write out the general forms of them first. So the easiest one of these two cases to write is the case where the answer is no. Which is to say that if we want to do a function to every element inside of a Prolog stream, but we don't have any elements, then the result of doing the function is to do nothing. Yes. So we'll then, there's another way to write this. I'll write this in a very direct way. No, I won't do it in a very direct way, actually. I'll quickly write the helper function that I need. Right. So fmap is, of course, this very common helper function that works across any type that is defined as being a functor. We'll say that if you're trying to map a function over a Prolog stream and the Prolog stream uh, has either a suspended value, or sorry, either a yielded value or it is simply suspended, in either case, we can use that function to apply to get a b out of the a value that might or might not exist. It helps to, I think, look at the type of this value, which is why I'm somewhat annoyed that it's not showing me that type, because it would be very useful to see. The gist of it is that it is of type suspend of a, so it's either a yield a, which in that case the a can be passed to this function, getting a b out, or it's a suspend, in which case we do nothing. Maybe that's useful. The next thing we do is we recursively call fmap over the rest of the list. Right. So the reason we use fmap, for what it's worth, to inject it into the rest here is because this is behind Prolog IO. Like, I can actually quickly define fmap Prolog IO, which should make this a little bit clearer. Right. So at this point, we happen to have a value of type Prolog IO. It lives in next. Oh God, what's it complaining about? It's complaining about a syntax error here. That'll probably expose where I've gotten myself horribly confused. Oh, it's not called next, it's called A's. Yeah, and it's not called PS, it's called P maybe. Look at all these changes that I've made that I'm not reacting to well. Oh, right, and we haven't defined the monad instance yet. That is, we haven't defined instance monad Prolog stream yet. We'll do that next. Cool. So anyway, yeah, we're going inside of the Prolog IO. I'll keep this name lying around because it's possibly useful to understand what's happening here. So the next one we'll actually be describing is the monad instance. Monad is technically anything that can implement monad can also implement applicative, which is to say that the functions in applicative can be defined completely from the functions inside of monad. We'll be taking advantage of that property in a moment. For now, we'll just say, we'll do these in tandem actually, because by convention, you would always write the phrase return equals pure because those functions are always defined the same way. The definition of pure is actually a little bit complicated. The gist of it is that we immediately yield the value x, and then we'll also define So you would never normally write these functions in Haskell because people would know what you meant, but there's no harm in writing them, and they might be clearer. Yes, so we've defined this pure function, and that says that we yield x, and then if somebody says, okay, but please do a little bit more compute and figure out if there's another value, we can immediately tell them that there's no other value. So pure x just immediately yields x. The other function is this one, which you've seen me define before. It helps to look at the type. It's called bind, for what it's worth. It's spelled this way because I guess that's a decision that the Haskell developers made. I can't give you any deep insight into why it's named this particular thing. I think that the decision to name it that is often criticized. But yeah, the gist of it is that if we want to do this function here to everything inside of an empty stream, the result would still be an empty stream. If we happen to have a value that we've gotten out of the thing, that's fantastic news. We would then respond by doing the function to the value. As a reminder, like this is all the invocation. I can make this a little bit clearer. That's the name of the function. That's the first argument. That's the second argument. Again, you wouldn't generally spell it this way in practice. And also, hold up, what am I screwing up here? Oh, wow, I've really screwed this up. Hold up a second. Excess. There. That's it. Yeah. Okay. So yeah, we've got this is basically still the form of a list. The first item of the list is actually here. This whole thing is the first argument of the function bind. This is the second argument, and it's just the function f. we would actually call the function f on the value that we got out of the stream successfully, and that we're happy that we got out of the stream successfully. And then we'd continue the stream. We can't actually do all the compute here. We haven't been given permission to do anything other than take the f off the top. So we have to produce a suspended version of the stream, which would just have the tendency to call f on all of the things in the suffix. Oh, what have I screwed up? Oh, that's right. I haven't defined that function yet. Okay, sorry about that. Well, all these things depend on each other, apparently, in the most awkward of ways. I'll come back to this and explain what that actually means above in a moment, but for now, we'll define a few other things. If somebody wants the empty Prolog stream, that's just defined as a stream that immediately says no. I'm sorry, that's not where that should be defined. That's where that should be defined. Okay, interesting. And yes, that should actually have the type of Prolog stream of A. You can always have an empty stream of any type. We can also define this function as going from two Prolog streams. Yeah, when I referred to what this function did and I hadn't actually defined it, that was probably pretty confusing, huh? We'll say that, yeah, if we have a stream that still has something in it and we want to merge it with the next stream, we would then say that the result of that is a stream where what's the best way to write this? Sorry, I'm trying to think about this. That's not actually the right type. This is the right type. Let's see. Merged would be written as what? It's something like this. Crap. What's the type of this? I'm already forgetting. Right. And let's see. That would be a Prolog stream of A. Maybe this actually isn't much clearer. Now hold up a second. Why the hell doesn't this work? I'm going to go with my previous implementation, and then I'll see if I can reverse engineer it. This is a much longer implementation. I was hoping not to bring in this lift M2 function. These functions are just horrible to write, for the record, in Haskell. It's very hard to get these right on the first or even like the 8th try. I mean, I'm fine with it being lift A2, which has the exact same behavior as lift M2. Let's write the other cases of this real fast, and then maybe it'll be clear how this is supposed to even work. Unfortunately, like, I've done my videos exclusively in languages where it's extremely hard to explain what's going on. But okay, the gist of it is that we'll go through the types because then I'll unconfuse myself. So XS is a Prolog IO of a Prolog stream of A. Next is a Prolog stream of A. Let's try the same refactor I just tried, and we'll see if that's any clearer. Might not be, who knows. So yes, we already have X's as a Prolog IO of Prolog stream of A. We already have next. That would be lift M2 is, I believe, equivalent to the following. This is, of course, not necessary to write for reasons that will be obvious. Okay, now I see where my problem was. Yes. So yes. Also, this can be made to be much shorter. The gist of it is that we're going to get every subsequent x out of XS. Or rather, we're going to... actually, hold up. I'm going to make a mess of this if I'm not careful. Or maybe I've already made a mess of this. Maybe there's something wrong with this definition. So the goal is to create a stream that yields everything from the left-hand side and then everything from the right-hand side in succession. I believe that's correct. So I believe that in that case, then yes, this is recursively calling down to this function. So we are, oh yeah, we are simply, it'd help to write the actual type here. As you can see, I have a hard time defending Haskell, and maybe the problem's not with Haskell, maybe it's with my brain. But I get terribly confused, and even when I think I understand it, I don't. The fundamental problem here is that we have two types that use the same trait, and all the names involved in the trait are in the global scope, and I therefore do not know which of these I'm calling until the last minute. Or actually, no, is that just the type? Oh, I'm sorry, we don't have scope to type variables, which is the language extension that makes it possible for me to write this. Or, do we have typed holes? I forget how we write this in a way that makes Haskell happy. Partial type signatures, that's it. Does that work? Well, okay, but Haskell hates it. But it also hates that. So what do I do with that? Scope type variables, I guess? No, it hates that too. What the fuck do I do with this information? It hates everything. What a good language. So I don't know. I guess I'll just leave it like that and I'll accept my stupid warning. Because it seems like I can't make it happy very easily. And there's probably a solution to this that I just don't know. And well, it doesn't seem like the tools are helping me. They're just telling me they're telling me to do things that don't fix the error. But yeah, this is all done in Prolog IO, meaning that the actual type of X is, yes, it's a Prolog stream of A. So we are in fact, I guess the right way to write this would be something like, X's future. Yeah. So okay. So we are getting the stream out of the box that hides the stream from us. And I would say that, like, yeah, the amount of fumbling I'm doing here is a little embarrassing and it gives me the temptation to posture about it. But I genuinely think there are very few people who could use this language and not fumble almost this amount over this kind of thing with an interface this confusing. So now we come all the way up to here. So the gist of it is that f of x will itself produce a Prolog stream. We know this to be true because f returns a Prolog stream, x is the thing that it gets out. So we're taking x off the top, and we're going to produce every result that f has for x. We're going to do all of these before we even look at the results that come from putting f, or from applying f to all of the other values that come out of this original stream. So this is the basic do with undoing operation, and I'll explain why this is a do with undoing operation once we get to reversibly and we see the structure of that. But I can't do that quite yet. We'll cover the final case of this really fast. So this is almost the exact same. The reason it's not the exact same is that we have nothing to actually apply f to. So we simply immediately go through the right-hand side of this. If you're wondering, by the way, I haven't benchmarked the performance of this. It's honestly probably pretty bad. But the performance that I would expect specifically here is that I would strongly expect Haskell to, like, these are mostly functions that recurse on the right side, which means they're tail recursive. So I wouldn't expect Haskell to actually burn a lot of stack space on these, which is great. It means that it probably compiles two functions that make fairly efficient use of a stack. However, you shouldn't trust me about that because Haskell is a tricky language and I could be full of shit completely. And how would I even know? And that would be worrying. Anyway, so we've got this beautiful instance of monad here. We did not ever finish our instance of applicative because we defined pure and we have the type here. We can just inject that type. We didn't define this yet. We're going to use a horrifying hack, or, well, maybe it's not horrifying, but I think it's horrifying. Like I said, the applicative interface can be defined in terms of the monad interface. This is one that it's good to stare at for a little while. So we're going to get, we'll name this in the plural. Right. So we're going to get all the f's, then we're going to get each x for every f, and then we're going to produce the f of x for each of these. I don't think this is that horrible when I look at it like this. For whatever reason, people who explain this trick will inevitably write it like this instead, which I think is scary. They'll write it like this. And it's like this, that means the exact thing, and it's technically slightly shorter. But would you ever actually want to write that? I think that most people who aren't, I guess, people who fully drunk the Haskell Kool-Aid would not prefer that. This is a fairly short way to write it. Yeah, so get all the f's out, then get all the x's out for each f. So that gets us, gosh, we've got so many of these. There's one more fucker that we got to write, if you'll excuse my language. So, and an alternative that's also a monad usually implements monad plus, which just provides extra sequencing operations that are substantially equivalent to the ones in alternative. This is not going to change your life in any significant way, but it might amuse you or make you satisfied to know that somebody anticipated that this type should exist. The reason that you would ever define monad plus as distinct from alternative is because Haskell has a variety of syntactic special cases for things related to monads that, for whatever reason, mostly don't exist for things related to applicatives. And therefore, it's like slightly more graceful to also have the monad interface. If you're like me, you might find that to be tiresome and silly. I certainly do. At any rate, so I keep promising that I'll explain how this interface allows for undoing, and I keep not explaining that. So let's quickly actually define reversibly. This one's not pleasant to look at, so I'll explain it. There might be a more pleasant way to look at it, but I don't know it right offhand. So reversibly will cause the stream to enter a specific succession of states. The first thing that the stream will do is it will suspend. The reason it suspends is because the base level Prolog stream can't do I/O before it produces a value. This is kind of why we have the suspend state, is because we frequently want to produce a stream where the very first thing it does before it produces a value is some extra I/O that we didn't anticipate when we were constructing this externally. So, okay, we've got this useful ability to suspend. We then take forward, and actually there's a simpler way to write this than the way that I've done it. I'm just seeing that now. We'll take v out of forward. Actually, hold up. This might actually... wait, is this actually a simpler way to do this? We'll try it the most overt way, and we'll see. There might be some reason this doesn't compile that I've yet to discover. So, okay, obviously that doesn't remotely compile is what I'm seeing here. And that doesn't surprise me that much. We'll write it the way that I did. Unfortunately, it looks very close to a standard pattern, but I think it's just not. I think because like we're mixing two monads here. So anyway, we suspend. The first thing that we do in order to figure out what the new Prolog stream actually is we invoke forward here, which we've now done. That gets us the value that was inside of forward the whole time. We might as well call that forward value. I say inside of forward, but like this is an arbitrary Prolog IO action. This could, for instance, be reading a file or something like that. And if it were reading a file, then forward value would be determined by the content of that file. Maybe that's what it does. Who knows what it does exactly? So we then would produce this new value, which is the new state of the stream, which is we actually yield the value. Somebody who's now happy with that stream can advance it. And the effect of advancing it, which is asking it for another solution, is instead of it yielding another value, we do the backward IO action, which is the reverse of the forward IO action, and then we produce no solution at all. We produce this, the empty value. So this has the effect of suspending once, which is not visible to a caller for reasons that we'll discover soon, yielding a value, and then when you ask it, it undoes whatever it did. So that's a very useful operation. That's kind of the core of Prolog. So I mentioned earlier that we don't see as the callers that it has suspended. We actually have to implement that behavior. So the way that we do that is as a bridge down to Prolog IO. So one second, this is going to be some real ugly code. So for one thing, we know that if our stream's already empty, we can just produce nothing. Oh god, I gotta type correctly or else I'll be in the shit. We got to do that. If it suspends but there's no actual value, we're just going to keep squeezing is what we're going to do. I can write this a little bit better. So this is again being done inside of Prolog IO. And I'll put it onto one line because I prefer these to be one-liners, but like I think that I'm slightly more used to reading these than you might be, so I'm being careful. Something that I'll frankly admit is that I'm probably overestimating how much better I am at reading these than, oh god, I shouldn't have hit the tab key. Sorry, I've been coding with AI at work. I'm forced to because of details of my job. And the tab key often just does the right thing when you're using AI, and then sometimes it just like deletes your file, and that's really shitty. I can get into my impressions of that, but I do think that it is both making me a better programmer in certain ways and a worse programmer in other ways. Anyway, oh god, am I actually going to write it? Is this seriously how I wrote it? This is a terrible way to write it. Maybe this is a slightly better way to write it. It does take a language extension. Yeah, no, we're going to do it like this. Or are we going to do it like this? No, I think we're going to do it with fmap. Right, so we're going to produce a tuple that contains just x, and then we're going to do the IO action that consists of the rest. I believe that's correct. Or no, we're not even doing the IO action that consists of the rest. We are just straight up... Hold up a second. I'm trying to figure out why the hell this code is correct. Like, I tested it enough that I think it is. I'm just trying to figure out... So this is in Prolog IO. That part I know. So this seems like it does more computation than it should be doing. So I think that actually there might just be a problem with my original implementation. No, I don't think that's true. I think unfortunately it has to do some of the compute involved in getting to the Prolog stream here. So maybe the actual correct way to do this is like this. Yeah, that's not at all how I implemented it the first way, but this doesn't do any of the compute associated with REST. It just maps it to a state where the value has been yielded, and it is therefore still suspended, rather than making any effort to get a value out of the REST. I think that I would be much more willing to defend this particular implementation than the previous one. Okay, we've done all of that. There's a few other things that we're going to quickly do here. I think I've mentioned that Prolog is about finding a set of solutions for the constraints we have, which basically means running to the point where we yield back to the caller. And then if the caller doesn't ever ask for any more, we just stop. We're going to encapsulate all of this Prolog gunk with thread type. So this basically represents a program that can... This represents a persistent grip on a Prolog program that can be advanced ahead. It encapsulates the detail of exactly how far the Prolog program has gotten, which is probably useful. The IORef type might look scary. It's just It is the way to put a value into a variable that supplies sequencing in or not in Prolog, in Haskell. The interface is actually really straightforward. It looks a lot like file I/O basically, except it's all done in memory and it's done really efficiently. So we define new globals and primitives. That's all true. Yeah, so this is going to look like a file that we can read or write to. It's actually just a variable in memory. Haskell will keep the sequence of operations that we imply via either do notation or the monad functions, which, as a reminder, do the exact same thing. That shouldn't be threads. That should just be a thread. Nice. So, okay. So, yeah, we have basically the instruction pointer, and then we have the globals that are always passed to the Prolog IO that is inside of the thing, which, as you'll remember, eventually we're going to put some useful Prolog related state into the globals that the Prolog IO uses. So the next thing we do, if we have the desire to do it, is we write a function that takes the next solution. So this will just advance the thread until it suspends again and get a solution out of it. All of that is just function to get the fields out of the value. There's other ways to do it, but that's a fairly direct way to do it. Like, actually, if I were to show off the way that somebody who isn't used to destructuring might write it, they'd probably write it something like this. We'll get back to a familiar function now. Wait, oh, yeah, that's right. We've got the thread globals and this variable now. And so we now put all of the state back into the file-like container that we have. You'll remember that one of the things that squeeze does is it actually returns the next state. So that, like, that's right there is the next state that it returns. Very cool. Well, at least I think it's very cool. So we get out the next value for the benefit of presumably our caller. The stream reference is, oh, hold up, right. There's a reason I put them into variables. I just couldn't remember what that reason was. Now I remember. Beautiful. And this is presumably useful to do. Right, so we'll take a solution, and the idea is that if this ever produces nothing, then it's never going to produce a value other than nothing. So we'll produce that value, and otherwise we will build a linked list containing all the solutions that there are. Now, note that because this is an IO of list of A, this is completely non-interruptible. Haskell has to actually, crap, the semantics might be more complicated than I think they are. But as far as I can tell, like, no decisions you make about how you consume the list will prevent the IO actions from occurring. The IO actions have to be done in order to get anything out of this. I'm not 100% sure that's true, actually. I'll have to think about the logic a bit. I think that if I expand it, it'll be more obvious what the deal is. Or I guess even if I just try it, but I believe that's how it behaves. It's worth screwing with. I think that this is for what it's worth. That's not a case where I would actually criticize Haskell. That's just a case where my Haskell knowledge is like not in itself sufficient to make good judgment. It's been such a long time since I seriously used it, and I wasn't good at it when I did use it. I'm just I'm getting rid of the weirdness that we've introduced for the purpose of making this file easier to read in a way that's unusual for Haskell programmers. So okay, that'll be all our functions. Let's quickly export a list of them so that we aren't exporting everything in the world. For one thing, we don't export the constructors of Prolog stream, so nobody can actually create a Prolog stream except via these methods of standard traits that already exist. Like they can call empty and that will get them one, but they can't call p maybe or p no. that's not allowed. Right. So that'll get us somewhere, or at least I think it will. Geez. So we've still got this primitives file, by the way. Is there anything here that we would actually export? I think new globals and globals we'd export actually. That seems useful. Yeah, Prolog IO that gets exported. Error prim that probably should be exported too, actually. So okay, we've done the non-determinism of Prolog. It'll be hard for us to actually practically use that at this time. You can presumably believe me that it works, but it might be more useful if we actually provide something that calls into that. So to that end, let's add a few primitives that are actually relevant to Prolog. So I said that we were going to build a store that basically tracks all the constraints that exist. The gist of how these exist is that we reuse our term type to represent a constraint. We'll look at the term type again in a moment, and I'll show you what it says. Oh, I actually have to... what? No, I didn't mean to do that. Right. So, okay. So we've got... oh, do I actually have to... Right, I have to import that. So term is defined as either a compound, which contains the actual value, or var, which is effectively a reference to... it is a reference to another cell in the int map. So if this is bound to a compound, that means that the term has a concrete value. If this is bound to var, it means that we don't know if it has a concrete value because we would have to check this other slot in the data structure. So that's like the cool property that we're using to track the values of variables here. And that means that like we can reliably, like if we wanted to represent 4 variables that all have to happen to have the same value, we just have them all point to the same leaf level variable, and that would do it. It'll be obvious why that's true when we write the function that accesses these. We haven't done that yet. We'll actually have 2 levels of accessors, and I'll show them both off. We're going to also track, because right now a variable is basically just a slot, which isn't very useful. We're going to also quickly track the names of the variables and the index of the next variable. The reason that we do this is because names are actually not unique across a Prolog program. To give a quick example of that, if I were to say friend, or let's use the archetypal problem. Or we'll just go with father of x. Father x of y is x equals Mike, y equals Carl. This is not the most common way to write this program. There's simpler ways to write it. But in this world, x is a variable that's defined twice. This gets a little bit worse when you consider the ancestor function. So, or sorry, the ancestor predicate, excuse me. So here, the ancestor function, or sorry, predicate might be called more than once. And the second time it's called, there's still a variable named x, but it has to be a different variable because we haven't, somebody isn't going to be their own father, and we need to call it such that the second person in the father relation, the son in the father relation, is now an x. So it's very important that these values be allocated basically on a stack basis. By the way, we're using the name for this. We might as well just say the name of the variable is also a string. Fun fact, by the way, because a string is a linked list of characters, this isn't usually how people represent strings when they write Haskell. They usually use a different data type, but I didn't feel like pulling one in for this one. I felt I'd just use the one that's in scope. So anyway, so we now have the ability to track what the names of the variables are, what their values are if they happen to have them, and what the next variable is. You can kind of think of this as having like an extra property, which is that if a variable is not bound at all, it's bound to the value of nothing, because that's what you get if you look up a value in a map that's not in the map in Haskell. Um, okay, new globals now becomes more complicated. We have to allocate a store for the values, which will by default be empty. We have to allocate one for the names, which by default will be empty. And we have to allocate one for the slots, which no, that one actually is 0. Sorry, that one's not empty. What am I saying? Apparently, I named it next var, not next ID, so we'll just call it NV after the state of Nevada, where I do not live. Oh, never do what I do. Pay attention to the code that you write. Pay attention to compiler warnings. Shame on me. So okay, so we've got this now. We're going to call this prim. The reason we're calling it prim as opposed to new var is because, one, it's defined on Prolog IO as opposed to being defined on Prolog stream. 2, for the other functions that we're going to define here, we're not actually going to do a lot of error checking. We're going to be doing the error checking in a separate re-exposure of these functions. This is just the bare bones do the work on the globals object functionality. Really feeling like it should be called slot, because that's the word that we used elsewhere in the program. That might be better. A lot of name collisions, huh? Excuse me? Oh god, I don't mean to... I really hate the tendency of this tool to do the most specific import possible and then not improve the import and instead import other modules when you are done with it. Like, I find that to be genuinely really frustrating. So we'll replace the slot with its value +1. And we'll, yes. And okay, I think it's fine to call that new var for now. So this is another operation that is reversible once a slot has been used. But once you've recursed back past the point where it was originally used, you would just tend to you would tend to be able to use it for something else, because all the bindings that could possibly involve it would have been reversed. So we're removing the name that we stored earlier, which we could have theoretically used for like debugging. There's actually no reason to return unit there. We already return unit from modify IO ref. Excuse me, that's a slot that we should be using. So we use maybe here. We'll get nothing if it's not actually defined, which is probably a useful behavior. Might be a useful behavior. Right. We'll look it up, and the lookup function returns nothing if it's not there. This is kind of the, what would the word be? This is the counterpart function. I was going to say inverse function, but that's not true at all. An inverse function looks like unnew var prim. And yeah, so outside this file, we're not going to expose the fact that Prolog.io is just an alias for taking this extra argument. That's not going to be visible in any way, because these functions actually do everything that we need. Right. So this would just say alter will take a value that's either nothing or something. And if it's nothing, it will just helpfully remove the item from the map. It's the most general way to modify a map. We can look at its type for a moment, and you can be very impressed by its type. By the way, if you're wondering why we're using int map, it's a special case of map that's a little bit faster than a standard map. But only if you're using the int type. If you're not using the int type, you're not allowed to use it. So we've got that. That's pretty cool. We can re-export these. Let's re-export these in approximate order. In this part, we've basically done all the hard parts, so it's just a matter of doing the easy parts. We've got to, let's see, we've got to track bindings, and we've got to do those on top of Prolog stream, which is to say that, like, the functions that I've just defined are not inherently reversible because Prolog.io actions actually can't be inherently reversible. Prolog.io doesn't have the backtracking functionality that we want. Backtracking was the word I was looking for. How silly of me. We'll be providing exactly these functions, which is not a lot of functions, right? It's the functions we got. There's other ways to define the interface to this kind of functionality, by the way. One of them is to provide a term that has syntactic placeholders that are strings for the variables that need to be defined with the new var function. But this is a lot simpler as an implementer. And if you didn't understand what I meant by that, don't worry about it. I'll point it out again when I get there, but it's not that interesting or useful a design decision to contemplate. So we'll be defining a new var function. It has the same type as the previous one. It's just unlike the previous one, it's reversible. Oh gosh, what's on fire now? Something's on fire. What'd I do? Oh God. Oh no. Oh no, the Haskell language servers absolutely, oh. I misspelled it. I totally misspelled it. Shame on me. And that just generates errors across the whole project. Again, if you want good error messages that make sense, I can recommend many languages that aren't Haskell. Don't try to write this program in Rust. You'd be miserable. You could probably write it in, no, you shouldn't write it in Java. That you'd be miserable for different reasons there. Like, as it turns out, Haskell's like sequencing operations and its traits for that are like, sorry, type classes for that are like this genuinely cool feature that no other language has. And I feel good things about it. Anyway, yeah, this doesn't need to be reversible because all it does is read something. So why would you, how can you reverse a read? I guess you can erase it from your memory, but that's about it. Yeah, so this is the exact same function as getVarPrem. Also, wait a second. What is the... Why does this compile? Oh, I'm being silly. It doesn't compile. Beautiful. We've got... Oh, I've yet to define these functions. I'm going to define them. I promise I will. I'm just getting blindsided by the fact that it's complaining that I haven't defined them yet. So a variable can also be set. This one's more complicated. The reason being that we have some error checking that I'd like to do. To be clear, these cases should never actually occur in practice. They can with some of the additional functions that most Prolog implementations come with, but you wouldn't be using that functionality on a daily basis, and you certainly wouldn't be using it for this particular system. This is a very simple system. Right. So obviously it hates that because I haven't, you can't end on pulling a thing out of a data structure. Haskell wants to know what you want to do with it. The idea is that if we're setting a variable that was already set by somebody else, we've probably done something wrong. This function can't be called directly. It's called by the new function that we're going to be defining in a moment. Likewise, we shouldn't be unsetting a value that's already unset because it makes no sense to do that at all. At least I don't think it makes any sense. Like in theory, the only things that can affect each other here are the two cases of set var. If you called set var prim directly, obviously that would bypass this. But in theory, this is the only thing that affects itself. And if that's the case, then we should be able to characterize its interactions with itself very exactly. There's really no branching. Anyway, okay, beautiful. So now we get to the first genuinely Prolog specific operation in the entire program. Like everything else we've written is very common to, I mean, this is also pretty common to logic programming languages, but we're getting into an operation that SQL doesn't have, that Prolog does. Remember that Prolog and SQL are relatives, but they're not close relatives. Some people would dispute that. I would say those people are wrong, but that's just me. So basically there's 4 cases to unification. I'll explain what unification is first of all. Unification is the algorithm that takes 2 terms, like we'll say hello, or no, we'll be more specific. Act, person, cook, and we'll say the other term is act, pyrex, verb. Unification is the system that takes this and outputs the following. And it does that right into the global state. That's what it does. And it has 4 cases, 3 of which you can actually see in this example. One of them is compound, which is implemented like this. The first one has type act2. The second one has type act with 2 arguments. Great. Next, we unify person, pyrex. And next we unify cook, verb. That's how we handle the compound case. So in the case where we unify person, pyrex, that is the var compound case. The way we handle the var compound case is that we figure out what the var is bound to and then unify between that and the compound. If the var is ultimately not bound to anything, we output person equals pyrex. The other case, which is very similar, this just defers to the var compound case. We implement this by unifying verb with cook, so it's the same as the previous case. And the var case isn't actually a separate case. It kind of follows from the other rules. We do have one specific rule, which is that we don't generate a constraint that says that a var is equal to itself. You'll see that in a moment. So to start with, we're going to check that, yeah, we'll do it like this. So empty, as you'll remember, is defined relative to the function. And if you don't remember how that function, the alternative function, is defined, we'll quickly look at it. Empty is defined here as no, the empty stream. So this will stop the chain of logic cold. It will basically make the Prolog evaluator go up to the nearest alternative operation because this stream is dead. It might be more obvious if I explain. Like if you imagine that, like, for A we have values x, y, z, and for B we have values A, or we'll try not to reuse letters. We'll say W, TUV. Okay, so beautiful. So these are, if we treat these as alternatives, like this, then we can say that we can say that if we were to replace one of these with empty, there would still be 2 elements in the stream. Now, on the other hand, if we were to require that there be a solution for each of these, let's say x substitutes for binding b equals 1. y substitutes for binding c equals 1, d equals 0. Or sorry, it substitutes for c equals 1 and c equals 0. And we say that operation z substitutes for this binding. Then the possible results at the various points in the program at x are b equals 1, at y is equal to b equals 1 and c equals 1, or b equals 1, c equals 0. At z, no possible values. We'll replace this with nil, or sorry, we'll use the same word, empty. Where to reiterate, like if this is done in the form of a series of alternatives, then these parts of the program effectively independently produce values. We would normally exit. 1 second, I'll clarify. Therefore, at a, no possible values. If we were to add to d the possibility to make a binding that says d equals 1, we would get something like this. And in that case, then also at a, these would be the possible values. However, if we assume that z is empty, then there's no possible values at a. However, if we do it like this, then a will produce solutions 3 times. So we would say at a after x, b equals 1. We would say at a after y, because x would have been reversed, we would have c equals 1, c equals 0, and at a after z, no more. So if z became empty, we'd still have 3 solutions. So the idea is that by empty, we cut off branches that look like an intersection, but we don't cut off the unions that contain those intersections, which might be an intuitive way to look at it. If that doesn't help you, you should play with Prolog for a bit, and you'll hopefully understand why it is that having one empty case in a predicate doesn't stop the predicate from producing results from its other cases. This is a case where I can only recommend playing with the tool because explaining it is a lot harder than seeing it in action. Anyway, we'll now go through the arguments pairwise. That's what form does. It's Haskell's equivalent of a for each loop. It's just a function, which means that it doesn't have the ability to do things like breaking. Like I can't write break and have form stop, which fortunately I don't need for this program. Otherwise it would be a real hassle. If you want a language that's like Haskell that has for loops that have all the features that you expect, again, Rust exists. So we special case the var case specifically by having it instantly, uninterestingly succeed with one result that creates 0 bindings. So this is succeed with no bindings. That's what we're doing here. So now we can write the other var cases in a way that doesn't genuinely strongly distinguish them from the previous ones. We'll start with the var compound case. Or rather, this is the var compound or the var case. But this is the var on the left-hand side case. So get var is, of course, lifted via lift prolog IO, but it doesn't do anything that needs to be undone, as you've probably noticed, because, of course, it doesn't. So that's very cool, and we like it. So if something's actually bound there, we would unify. And if nothing's bound, we would set the variable directly. We've hit the bottom of the pile. As a reminder, this is the place where we would undo the binding if we were going backwards over it again. The gist of it is that when we've reached this case, then this becomes one of the things that will be fetched from when we backtrack from the stream, or backtrack through the stream. And the reason for that is because we've defined the set of values in the stream, namely here and here, in a way that entails that backtracking actually be done. For instance, like if the stream once the stream has produced a value, we say now get the rest of them. And when it produces no values, we say don't. So the reason that backtracking tries to get the rest of them is that this case specifically says, well, now that you've seen the value, get the next one. This, as you'll remember, is exactly the function that's called when we use this function, the bind function. This is exactly equivalent to, I mean, I'll just do the rewrite for you. And because we've defined this function in such a way that it will attempt to get every solution for the first item in the stream first, we know that it will attempt to get all those solutions before it even starts on the next item of the stream. So we've written our backtracking rule. I'm just trying to make sure that you understand that that backtracking rule is why the backtracking is done in the way that it is, and in the particular order that it is, where this is undone before this is undone, and this is 100% definitely undone. Anyway, we've got one more case. This is the not necessarily a var on the left-hand side case, because if it were a var on the left-hand side, we would have covered it with this case. So now we know it's not. Oh, sorry about that, yeah. This is a fancy way to say T1 happens to be this, but, you know, use the entire term. Don't just use the arguments of the constructor. We can likewise write it like this. Yeah, so that gets us all the cases on Unify. The very last thing, this is just a visual convention thing. It's also often done in the foreign function interface of Prolog. So because of the way that Unify works, if a term is bound, Unify will always regard that term as being bound. But sometimes you want to convert a term to a form where it is very visually bound, where like the actual variables in its definition have actually been replaced. For instance, you might have these two that are equivalent. So that's artist x equals Da Vinci. So these two representations will 100% be treated the same way in all cases because of the way that Unify is defined. Like, it is impossible to operate on x without first figuring out what x is bound to. But if you were to return the term from your program, you might want to instantiate it. You might want to fill in all the holes in it. And therefore, we're going to write a function to quickly fill in all the holes. The nice thing is that it doesn't have that many cases. You'll notice that despite the fact that this is written in Prolog stream, it can only return once, because, and it can't return 0 times either. It will always produce a value. That just happens to be because get var can't fail. Well, it can fail. It takes down the whole program when it fails. If the program hasn't been completely taken down, this will produce exactly one value. Obviously, there's nothing stopping any part of the program from throwing a massive error that kills the whole program. It's just debatable whether you consider that to be part of the idea of whether it returns a value. It's certainly not part of Prolog's model of backtracking that you can set the computer on fire if you want to. So mapm is another way to write the same thing as form. Mapm is just form with the arguments in a different order. It calls the instantiate function on each arg individually. But it does so with the sequencing operation in between. So mapm will take all these Prolog streams of a term and produce a Prolog stream of a list of terms. And then this little right arrow, as you'll remember, is exactly equivalent to writing this, which is to say that ultimately we're taking the value that comes out of it and we're calling Haskell's sequencing operation that is flashy and built into Haskell. This type's a little scary, but T is usually equal to list, so this usually just operates on a list. Yeah, which maybe that's your thing, you know? Very cool. So, oh god, this file is apparently, oh, I've done terrifying things in this file. What have I done? What have I done? This is horrifying. Why is it so mad at me about everything? This is awful. What did I do? Oh, I didn't import all my things. Well, how's that going to work if I don't import all my things? Oh, foolish. Import control monad. That'll help. Oh god, why wouldn't this work though? This looks like it should work. Am I tripping? This looks like it should work fine. What did I do wrong? Set var prim. Okay, that's a Prolog IO. That's what I would expect to have. Yeah. Oh, did I forget to actually? I forgot to actually put the variable in here, didn't I? Like, how's it? Oh, yeah. There. Also, I named it var when it should definitely be named slot. That'll happen, won't it? You'll notice that these are almost exactly the same code, incidentally. They just They ultimately, one of them will take a thing that's empty and put a full thing in it, and the other one will take a thing that's full and put an empty thing in it. Isn't that poetic? Empty, that is 100% defined in control.applicative, I'll have you know. Yeah, this is where we find out that my code is not resilient against the bugs that I create in my own code. Unity, indeed. Oh, apparently I still think I'm writing a language that uses commas in like the normal way that you see a language use them. Beautiful. Okay, so now we've got unification. That should work great. There's basically one other thing that we need to do to get Prolog working. And that's to have a representation of the entire program. So right now we can unify terms, which is this basic operation that Prolog has to do. Prolog has to like take two terms and figure out what constraints could make those terms match each other. But we don't actually have the ability to write a program that would force such a thing to happen. So I'll just quickly represent a program. We'll just say that our representation of a program is a list of clauses, where a clause takes a term and maps it to some more terms. We'll say that a database consists of a list of clauses. A database is the word that Prolog programmers use for Prolog programs. You might find it surprising that I am using a Prolog stream of clause here because, like, you'd expect the Prolog stream to be introduced at another point. The reason I'm doing this is because a clause can have variables in its head, and we actually need to make those variables exist in order to see if they unify. We don't have to worry, they'll go away if we fail to unify because backtracking forces the variables to go away. But like, we have to have them to inspect the clause. Something that you'd normally see a Prolog implementation do is it would sort the clauses by the functor, which is sorry, not the functor. What's the word they use for it? Maybe it is the functor. Basically, so if you have a predicate that has, I don't know, this structure, act, person, behavior, this would be consolidated under a sorting key, act2, or a hash index key or something. And this clause would actually be something like, you get something like this. It would still have this type actually. So that would be like a normal way to do it. There's nothing wrong with doing it this way. I just didn't want to do it for this program because it would make the video longer, and the video is already really long. Apparently the video is like 2 hours now. Wow. We're learning a lot. This is going to be an alias for the function that I'm about to write in a moment. It just makes that function shorter. Basically, you might, very often if you're calling into Prolog externally, you will want to instantiate a term once you've made the term. For the reasons that I talked about, like it's helpful for something like artist x equals Da Vinci to be turned into a self-contained artist Da Vinci. And indeed, like that's what you would normally see in the debugging output of a Prolog implementation. So seeking is easy. We seek a goal is what it's called. A goal is what, like, when you call a Prolog predicate, you are doing so by giving Prolog a goal, and it's trying to prove the goal. That's the verbiage that a Prolog programmer would use for this. So the gist is that, and this is going to look a little weird. This is how you would say try all alternatives. So folding that over empty. Let's say that we had, let's say that we called this for x, y, z. That would be equivalent to x, y, z. Oh, my keyboard is in Korean now? Why is my keyboard in Korean? Oh no, it's in Russian. Why is that? That's weird. I don't speak Russian. Yeah, okay, my keyboard's no longer in Russian. So that's what this is equivalent to. So that's probably more straightforward than it looks if you've never written Haskell before. You can tell my ability to talk is going down. This is worrying because I haven't finished the video yet. So the gist is that the first thing that we attempt to do is we attempt to make sure the goal matches the head of the clause, because if so, continuing to attempt to unify would get us somewhere. Like, if it doesn't match the head, then we've basically already failed. We are doing this in alternative because any clause could potentially produce results. They all succeed or fail independently of each other. But once we've met the head for one, we now know that all of the other conditions also have to be met. So these new conditions are other things that we search for using this exact same seek predicate. This is the main place where recursion becomes possible in Prolog. And the recursion is, of course, tail-shaped in the last goal, but in the previous goals, it's actually no, it's never exactly tail-shaped because you're always producing choice points. That is, it always can backtrack past the point that you're at. So I guess like even though it looks tail-shaped here, it's not actually tail-shaped. Beautiful. Anyway, we've now got a representation of the database, so now we have to figure out how to actually call into this. So let's quickly, I've got a demo program here. I'm just going to move as quickly as possible towards having it run. You might object that at no point have we done anything that resembles a parser. Parsing Prolog is not actually easy, especially if you're parsing it correctly, but even parsing it wrong is kind of tricky. There's actually quite a few cases. So yeah, I do like parsers, and eventually I might show off how I write one, but I wouldn't do it in Haskell because I don't actually, despite the fact that a lot of people really like parsing in Haskell, I actually really don't like parsing in Haskell. They're ostensibly very good parsing libraries in Haskell, but I find them very frustrating because they are kind of black box-like, and Haskell programmers really don't like writing lexers for reasons that I understand but disagree with. Haskell programmers also tend to like parser implementations that can do an arbitrary level of backtracking, which I believe is almost always the wrong approach. Yeah, we'll just do it like this. So we'll actually implement the demo program shortly. I guess I should at least make sure it has the right type though. So we'll quickly say that this has type of Prolog stream of empty solution, which, you know, that's probably cool. Obviously that doesn't work yet. We'll do that. Okay, cool. And geez, this tool is going to kill me, I swear. I hate the way that it suggests these things. So yes, this demo program, yes, simply produces hello Haskell in a very complicated way. That's all we can hope for. Next up, we want to actually, we'll write the clauses in a moment. Let's first of all figure out what the program does. So I've used this example a few times. We're going to be figuring out what actions are taken by ostensible agents in an ostensible agent system. And maybe we find it useful to do that. This is, of course, no more or less silly than the vast majority of Prolog programs people write. By the way, the quote mark means new version of the variable. It's just, Haskell allows you to put apostrophes in identifiers, which some people overuse and I possibly underuse because I'm used to languages that don't have that feature. I can't adequately explain why that feature exists. I think it's just because Haskell is very popular with people who like math, where this is a common convention. Oh, what I do? Oh, I silly me. Yeah, I didn't actually use the sequencing operation. Now I've used the sequencing operation. So the immediate behavior of this program should be to fail to prove that anybody takes any action. That is exactly true. So we'll start with a very trivial example of an action that somebody takes. We will, and apologies, you're going to hate the way this code looks because our implementation is nothing if not verbose. So this is a clause saying that the actor of the name Sam goes to law school. That is what it does, and we'll also say that there's no arguments to that, or there's no further. There are no goals that are further associated with this clause. This clause only has a head. What I screw up? Oh, I see what I screwed up. Right. So that's probably pretty cool. We should be able to see that. Yes, Sam goes to law school. This is equivalent, albeit verbosely, to writing act Sam goes to law school. So next, to do a little bit of follow-up on my general themes, we'll say that there are certain actions that are vampire behavior. As a vampire, I might do these things. So one of the things that a vampire might do is drink blood. And that would look like this. And there's nothing else associated with this clause that could complete it. There are no other goals to seek. We'll further say that a vampire might spit venom. So adding these doesn't actually change the behavior of the program because nothing's linked to them. But something that we can do is we can add logic that says that, let's do it like this. So there is a person who is the actor. That goes in a variable. There is an action. That also goes in a variable. And we will say that and I'll rewrite this in conventional Prolog in a moment because it might be hard to see how this is just standard Prolog. I promise you it is. I wouldn't lie about that. Right. So we've done this. This doesn't actually add anything because, yes, nobody is eligible for this. But effectively what this says is right. And now what we'll do is we'll further add, oh, you'll have to excuse me. I have to, oh God, how did I screw this up? There it is. That's where it goes. Sorry, nobody on Earth likes parsing these. Haskell results in a weird amount of code that I find just extremely difficult to visually parse. But in this case, it's completely my fault. Or at least that's what I'll tell you, and you can see if you agree with me about that. So Nyogmi is a vampire. That's what we're saying here. Yes, we've now expressed that in Prolog, which means that, as you can see, Nyogmi now drinks blood and spits venom. So we can define vampires in a variety of ways. One of the things that we can add is this assertion that, yes, there can be a progenitor, there can be progeny. This is, again, simply feeding our very verbose system to create new variables. So we're going to rule on whether the progeny is a vampire. We're going to make that ruling based on, one, does the progenitor relation exist between the progenitor and the progeny? And two, is the progenitor actually a vampire? Which, is a valid question, because if I were your progenitor but I'm not a vampire, then that would not make you a vampire either. So we'll then say that Sam is Alex's progenitor. So I've now written that. So that doesn't actually matter. One, I need to spell Sam consistently. I'll do that. Not that it matters because those clauses don't talk to each other, but just for the sake of consistency. So it doesn't matter that Sam is Alex's progenitor because Sam isn't a vampire. If we make Alex a vampire, we'll start to see Alex is doing vampire stuff, but that doesn't actually affect Sam in any way. Now, because Sam is a vampire and Sam is Alex's progenitor, this should rule on both Sam and Alex. Yes, as we can see, it has ruled on both Sam and Alex. They are both vampires now. Yes. So this is the way that the logic works. And I'll just rewrite this one also in Prolog conventional syntax just so that you can see what it's expressing more clearly. Um, right. So that's the logic that we got. I can do the rest of them if I want to, but it'll be pretty verbose, so I won't bother. So what we have here, if I can brag a little bit, is we have a reasonably accurate implementation of Prolog done very directly in Haskell and using primarily Haskell's built-in sequencing operations to do all the heavy lifting for us. I don't think you can write this program in any language other than Haskell that isn't like derived from Haskell in some way, which is kind of cool. But also, like, look at this fucking code. Who would want to ever read this shit?